Hello everyone, welcome back for the second video on the imaging in real calculus or fractional calculus. Okay, so to start, I'm gonna discuss a specialized functions called Mittag-Leffler functions, and it occurs a lot in fractional calculus. And so here is how I define this. So the Mittag-Leffler functions. So basically, this is the function that you could write other function in terms of this function. Okay, so this is a more general function than the function that you are familiar with. So denote that by e, and then you have two parameters, alpha and beta, and then the argument is going to be z. Okay, and it's defined as a infinite sum, k going from 0 to infinity, z raised to the k power divided by the gamma function. And in this case, it's going to be alpha times k plus beta. Okay, so you see the beta, the alpha and the beta, that's where the placement of it. And of course, the gamma, some of the property of the gamma function is that, so the gamma function of n plus 1, let's say, is equal to the n factorial. Okay, and remember n factorial is n times n minus 1 times n minus 2, so on, all the way down to 1. Okay, so let's see if you remember any of these function that you've seen before. So for example, if alpha is equal to 0 and beta is equal to 1, so you have e 0 comma 1. Okay, so just write down the function. So it's an infinite sum going from 0 to infinity. You have z to the power k. And then inside this gamma function here, you have 0 times k, and then plus 1. Beta is 1. Okay, so gamma of 0 times k plus 1 is the same thing as gamma 1 for any given k. Okay, so this is by definition equal to 1. So what you're left with is this. It's just an infinite sum of from k going from 0 to infinity of z to the raised to the k power. Now, if you want to write this out, you see for k equal to 0, you have z raised to the 0 power, and then plus z raised to the first power, plus z raised to the second power, and so on. Okay, so z to the 0 power is just 1, so this sum is just 1 plus z squared plus z cubed, and so on. Okay, so we see here that this is nothing more than just a geometric series. So this is equal to 1 divided by 1 minus z. Okay, provided that the magnitude of z is less than 1. We need this so that this expression would have convergence properties. Okay. All right, so the next one is probably a function that you guys are familiar with. So what happened when alpha is equal to 1 and beta is also equal to 1? Like this. So alpha is equal to 1 and beta is equal to 1. Okay, so according to the formulas, there's an infinite sum going from k from 0 to infinity, z to the k power. Then you have divided by the gamma function. So 1 times k plus 1. Okay. So 1 times k plus, okay, so gamma of 1 times k plus 1 is the same thing as gamma of k plus 1. And by definition of the gamma function, gamma n plus 1 is equal to n factorial. So in this case, it's going to be equal to k factorial. Okay. So I'm replacing the sum here. K is still going from 0 to infinity. You have z to the k power. And then you have k factorial. Okay. Ta-da! This is equal to the exponential function of z. X px of z. Or sometimes you could write it like this, e to the z power. Okay, so e, so this is the Mittag-Leffler function, 1, 1. Z is equal to the exponential function of z. Okay. So let's do another one. Let's see. What happened when alpha is equal to 1? If alpha is equal to 1 and beta, let's say, is equal to 3, let's say. Okay. So then you have the Mittag-Leffler function. So it'll be 1, 3. The argument is still z. Okay. So sum going from 0 to infinity. I have z raised to the k power and divided by the gamma function. So the gamma function here is 1 times k plus beta, but beta is equal to 3. Okay. So this is the same thing as k equal to 0 to infinity. Z to the k, and then divided by gamma k plus 2. No, plus 2 plus 1. Do 1 plus. Yeah, so this is a gamma k plus 3. And so that is just k plus 2 factorial. Okay, so rewriting this sum as k from 0 to infinity. I have z to the k. And gamma of k plus 3 is the same thing as k plus 2 factorial. Now notice I have k plus 2 factorial in the denominator, but I only have k on the top. So I need something like k plus 2 to match that. So what I'll do is I'll multiply the top and the bottom by z squared. Okay. So it's the sum, k, 1 from 0 to infinity, z squared on top, and then divide by z squared at the bottom. Then I still have z to the k power. Okay. Then have k plus 2 factorial. Okay, so you see the power of z to the 2 power and z to the k. I could rewrite it as one term. So I'm going to factor out the z squared to the front. So 1 over z squared times the sum. Okay, going from 0 to infinity. The top is z to the k plus 2. And then divided by k plus 2 factorial. Okay. So you could write this sum out if you want to. So for example, what happened when k equal to 0? Well, when k is equal to 0, then you have z squared, z to the 0 plus 2 divided by 0 plus 2 factorial. And then k equal to 1, then you would have plus z 1 plus 2. Down here is 1 plus 2 factorial. So essentially, what we have here is 1 over z squared. And here, the first term here is you have z squared to the 2 factorial. And then the next term is z cubed to the 3 factorial, and so on. So remember, if we want to complete this, going from 0 power of z to the n power, what you're gonna need is you're gonna add 1. Okay, you're gonna add 1 here. And then you're gonna add the linear term, so plus z. So that means over here you have to subtract 1 and then subtract a z in this series. Okay. So you see this part right here is 1 plus z squared plus z cubed. That is just the exponential function times e to the z. Right? This is the exponential function. And then minus 1 minus z. Okay, so the Mittag Leffler function e1 comma 3 is that object. So the components that you are familiar with is the exponential function here, e to the z. Okay, next we'll try something a little bit harder. What happened when alpha is equal to 1 and beta is equal to m? Beta equal to m, where m is an element of the natural numbers, integer. So I'm gonna write down the Mittag Leffler functions, 1 comma m, with the argument z. So what is this function? All right, so I'm gonna start with the sum, k going from 0 to infinity, z to the raised to the k power, and then divided by gamma of 1 times k. That's alpha times k plus beta, and beta is equal to m. So this is what I have. Okay. Okay. Yeah, so let's just write this out for k equal to 0 and see what happened. So I'm going to have any m plus 1, m minus 1 there. Okay. So let me just complete this. This is the infinite sum k from 0 to infinity, z to the k power, and then gamma k, and then divided by gamma k plus m. Okay. But that is nothing more than just k plus m minus 1 factorial. Okay. So you have the sum going from k 0 to infinity, z to the k. This is k plus m minus 1 factorial. Okay, so the trick here is you have the k plus 1 minus k plus m minus 1 factorial down here. So you need something that looks like the power of the denominator upstairs so that you could combine it so that you can make an exponential function out of it. So one way to add the m minus 1 is to divide by a z raised to the m minus 1. Okay, so k equal to 0 to infinity. So I'm multiplying z raised to the m minus 1 divided by z m minus 1. Okay, this is just 1. So z raised to the k divided by k plus m minus 1 factorial. All right, so I'm going to factor out the 1 over z to the m minus 1 outside of the sum. So 1 z to the m minus 1. Sum k go from 0 to infinity. And the top here is just z of k power plus m minus 1 divided by k plus m minus 1 factorial. And so you see here the power of the z in the numerators is the same as the factorial factor downstairs. So this thing here is nothing more than just an exponential function plus some other stuff. Okay, so let's just write that out. So 1 over z to the m minus 1. So let's start with the k equal to 0. What happened to this term here? So then I would have z to the 0 power plus m minus 1 divided by 0 plus m minus 1. And then the next term, z 1 plus m minus 1 divided by 1 plus m minus 1. And then the next term, k, when k equal to 2, z 2 plus m minus 1 divided by 2 plus m minus 1. So you can see the pattern, okay? So let me rewrite this. So it's going to be 1 over z to the m minus 1. The first term in the bracket is just, the top is just z to the m minus 1. Downstairs is m minus 1 factorial. And then the next term is, you see the 1 cancel this minus 1 here, so you have the z to the m term divided by m factorial. And then the next term is going to be plus z to the m plus 1 divided by m plus 1 factorial, and so on. All right, so the only thing that is missing in here to complete, to make it an exponential sum is going to be, I need to add in, let's see, so the 1 over z m minus 1 is in the front here. So I need to add a 1 here, a z term, plus z squared over 2 factorial, z cubed over 3 factorial, and I need to go up to z to the m minus 2 plus z all the way up to z to the m minus 2 divided by m minus 2 factorial. And then the next term would be this thing here in the bracket, minus 1 over m minus 1 factorial, and so on. Okay, since I'm adding these terms into this bracket, I have to subtract the same thing. I can't just add this to it. I have to do the same to compensate that. So I have to minus a 1 minus z squared over 2 factorial, all the way up to minus z to the m minus 2 divided by m minus 2 factorial, close bracket. All right, so rewrite this 1 over z to the m minus 1. Okay, the top here is just an exponential function, e to the z, and then I have minus 1 minus z squared over 2 factorial, all the way up to minus z to the m minus 2 divided by m minus 2 factorial. Okay. So I'm gonna rewrite this in more compact form. This is going to be equal to 1 over z to the m minus 1 times e to the z minus, okay, still going from 0 to not to infinity, but to m minus 1, m minus 2, I mean. Okay, so I would have this z to the k divided by gamma of k plus 1. Okay. And that is, so this would be this would be equal to the mid-tag function of alpha equal to 1 and beta equal to m with the argument z. Okay. Okay, now let's take a look at some other functions, like a trig function or hyperbolic sine or cosine. Just remind you, the hyperbolic cosine is this. So cos of z is a sum, okay, going from 0 to infinity again, z to the 2k divided by 2k factorial. Okay, so this is a hyperbolic cosine. Hyperbolic cosine. So let's see what mid-tag functions would correspond to this. Let's see here. How about e to the 2 to the 1? So alpha is equal to 2 and beta is equal to 1, and then z. Okay, so let's see here. It's k going from 0 to infinity. Then I have my z here. Z to the k power. And then divided by gamma. Remember, gamma of alpha times k. Alpha is 2. So 2k plus 1. Okay, so the denominator is going to give you z to the k. Denominator is going to be 2 to the k factorial. So you see the power in the numerators is k. So we need like a factor of 2 here. Okay, so what I could do is I could rewrite this as k going from 0 to infinity, z to the 1/2. In other words, take the square root, and then take the square of z. Okay, so now I have some object of z to the 1/2 raised to the 2 power 2k. So divided by 2k factorial. Okay, and that is the So that is kind of like the series that you see up here, except this here is now equal to hyperbolic cosine of not z, but z to the 1/2, or the square root of z, cosh, and the square root of z. Okay. So the mid-type function e to the 2 comma 1 of z is equal to the hyperbolic cosine of the square root of z. Okay. Okay, let's try another one. What happened if alpha is equal to 2 and beta is equal to 2? And then we change the argument. Instead of z, we're going to have z squared. So the mid-type Leffler function, 2 comma 2, and z raised to the 2 power. Okay. All right, so this here, I'm just gonna write in the infinite sum, okay, going from 0 to infinity. I'm gonna have z squared raised to the k power, and then the gamma function is gonna be 2k plus 2. Okay. All right, so this right off the bat here is just k equal to 0 to infinity, and then the top is going to be z to the 2k, and then the bottom gamma of 2k plus 2 is same thing as 2k plus 1 factorial. 2k plus 1 factorial. Okay, so you see the power of the z term in the numerators is just 2k, but downstairs is 2k plus 1. So I have to multiply a z and divide by a z. So I'll put a z, put the z, 1 over z in the front, and then I have k equal to 0 to infinity, and then I have z times z to the 2k divided by 2k plus 1 factorial. So this is equal to 1 over z, and then the top is going to be z to the 2k plus 1 divided by 2k plus 1 factorial. Okay, since the form is the same in the denominator compared to the numerators, this is going to equal to the hyperbolic sinh. Okay, so this here is a sinh function. So 1 over z to the sinh of z. Okay. Also to remember, the sinh has a power series. So the sinh itself, sinh z, has the power series as k equal to 0 to infinity z to the 2k plus 1 divided by 2k plus 1 factorial. Okay. So there we have it. The mid-type function of e 2 comma 2 of z squared is equal to 1 over z times the hyperbolic sine of z. Okay, so essentially you could write any functions, trig functions, in terms of the mid-type Leffler functions. So guys, as you can see, You could write any transcendental function or trigonometric functions in terms of the Mittag-Leffler functions, and it's going to be a common occurrence in fractional calculus. So that's I hope that's a good intro to the function itself. And next time, I'm going to do take derivative and integration of these functions. Okay, so that's be on the next videos.